यहीं से पता लग जाता है। Good evening, students. Let us just revise what we have done till now. So we started the chapter work, energy and power with the scalar product. So in physics we need to learn vector algebra, little bit of vector algebra, in which there is addition of vectors and multiplication of vectors. So addition of vectors we already did. So geometrically we can add the vectors by triangle law and parallelogram law. And also if I want to find the magnitude of the resultant, you know that this is equals to under the root a square plus b square plus 2ab cos theta. And I can also find its direction alpha. So that we know. Now here we need to learn how to find the product of the vectors. So product of the vectors in scalar, there is only one type of multiplication. 3 multiplied 2 is 6. But here in vectors, when we are finding the product of vectors, there are two kind of products. One is scalar product and another is vector product. In scalar product, so here so students, we have done addition of vector already, and multiplication of vectors are of two types, scalar product and vector product. So in scalar product we have a dot over here. In vector product we have a cross over here. So dot product, the resultant is scalar. In cross product the resultant is vector. Now the formula for work done is when the force is constant. We already done this, force into displacement. So this force was in the direction of the displacement. So now if this is the angle theta between the displacement and the force, then the component of the force in the direction of d is fx, and fx is equals to f cos theta. And now this thing can be written as this. So this is the vector way of writing f cos theta into d, or you can say fx d. So students, just understand this thing, that f dot d is nothing but you are writing fx d, you are writing f cos theta into d, or you are writing f dot d. These three are the same thing. So we will be using this dot product notation now. So that is for the constant force. When you have applied the same force throughout the displacement, but when the force is varying, then the force is variable, then the work done is, so initially I started with xi initial position and I moved the object up to final position xf. So I have applied the force from xi to xf, and this is a displacement. So f dot dx is equals to work done. So this formula is there for the variable force. So these are the limits xf xi for this change dx. So always remember, these are the units, these are the limits of x position. And then we did the scalar product more in depth, a dot b. So this was a in 2D, I have written, you can write it in 3D also. And then multiplying it like we are multiplying x plus 2 into y plus 3. So you are distributing, so using distributive law. So here also it's the same thing, axi dot bxi cap. So axi cap dot bxi cap, axi cap dot by j cap, and this way we have I dot I cap dot I cap is 1 into 1 cos 0 1, and similarly for j dot j, and similarly for v dot v. But if the angle between the vectors is 90 degree, then this dot product is 0. So I dot j is 0. So this way we have done the scalar product, and then we did a numerical based on it, in which theta was asked. So f dot d, we have written f dot d as fd cos theta, that is equals to fx dx fy dy plus fz dz, because I dot I will be 1 and I dot j, I dot k will be 0. So out of 9 terms, only 3 terms are left, and we just put the value of fx dx. So fx dx 15, fy dy 4 for the 16, and fz dz minus 5 into 3 minus 15. And then written the value of magnitude of f, magnitude of d, and then that we have found. So f is equals to under the root fx square plus fy square plus fz square, and this also displacement equals to under the root dx square plus dy square plus dz square. So now for the next topic, we did work energy theorem. Work energy theorem says that change in kinetic energy is equals to the work done. So we started with the equation of motion in a straight line and multiplying m by 2 both sides, and this becomes final kinetic energy minus initial kinetic energy is equals to m into a is f into s displacement, and f into s is work done, and final minus initial is change in kinetic energy. Now if it is motion in a plane, then in vector form we can write this equation as in this form, and then again doing the same, multiplying both sides by m by 2, and we have found the delta k is equals to f. So that is the work energy theorem we have proved. Now that this is for the constant force, and now for the variable force we have k is equals to half mv square, differentiating both sides with respect to t, and we got here. So look here, I am differentiating v with respect to t. So if I differentiate with respect to v, then it is the power becomes the coefficient and power reduced by 1. So we know this, that in general form we can write it as d dx, and dx raised to n is equals to n into x raised to the power n minus 1. That is the formula, you can say. So this formula has been used here. So, and then you can write further the derivative of this base. So that can be dx by dx, and dx by dx we need to write that is equals to 1. So that's equals to 1. But here it is t, so differentiating with respect to t. So here base is v. So first step will remain the same, bringing the power as coefficient and reducing the power by 1, that is 2v, and then differentiating the base with respect to t, dv by dt. So that's how. So 2v into dv by dt, half m is constant, comes outside. Now this comes out to be dv by dt is acceleration, and that's equals to m into a into v, and this comes out to be f into dx by dt. Now another way to write it as, you can remove dt dt, so this will be dk is equals to f dx. We have not cancelled out, no, this is another way. Same means both the things are same. Now integrating both sides, so here there is change in kinetic energy, so I need to take the limits of kinetic energy, initial kinetic energy to final kinetic energy. Here it is displacement, so I need to take the units of displacement sorry, limits of displacement xi to xf. So at xi the kinetic energy was ki, and when at xf the kinetic energy is kf. So students, we need to be careful about this lower limit, this upper limit. So we need to write the limits about what the change we are talking about. So this k equals to this integration of dx is x plus constant of integration if it is if there is no limits, but here I have the limits. So this way, now dx, its integration is x. So we can just remember this thing, that integration of dx is equals to x. Now it's definite integral, so put x equals to xf final value minus put x equals to xi, and then for dk, if instead of x it is dk, same thing, integration of dk is k, and then so if you want to know that why it is this, then let me write the formula. X raised to the power n into dx is equals to x raised to the power n plus 1 divided by n plus 1. So that is the formula for integration. So here in this case you can assume that this is x raised to the power 0 into dx. So x raised to the power 0 into dx, so increase the power by 1. That is what integration is. So 0 plus 1 is 1 divided by the power 1. So that is equals to x. So that is why integration of dx is x. So similarly, integration of dk is k, and then put k is equal to kf, and then k is equal to ki, kf minus ki. So integrating this side, and see, this is the formula of work done for variable force. So that is equals to W. That is the definition of work done for the variable force. And here put the value of k is equal to k, final value by initial value, that is equals to, so delta k is equals to work done. Now we did one example 6.2 in which the drop was coming down, and there is this drag force which is resistive force directly proportional to the speed. So more is the speed of the drop, and then more will be the resistive force. So that's what the question was about. So here we need to find out the work done by the gravitational force and work done by this upward resistive force. So we, by the work energy theorem, we know that change in kinetic energy is equals to work done. So what is change in kinetic energy here? Kinetic energy final minus initial. So drop is coming down, so it came down from the height of 1 kilometer, and 1 gram is that is equals to 10 to the power minus 3 kilogram, 1 gram. So that is the mass of the drop, and it came down from height of 1 kilometer. So initially its velocity was, so it was in the clouds over here, so initial velocity was 0, and final velocity is 50 meter per second. So final kinetic energy minus initial kinetic energy. So we have found putting the values of v and u. So u is 0, so this term will become 0 and half mv square. So I've calculated change in kinetic energy is 1.25 joules. Now work done by gravitational force is given by mgh. So, and the work done is equals to 10 joules. So now the total work done is work done by the gravitational force plus work done by the resistive force, and that is equals to delta k. So delta k is equals to work done, and the work done here is W, work done by the gravitational force acting downwards, and work done by the resistive force acting upwards. So what is work done by the resistive force equals to the Wg will go this side, and this will comes out to be W minus Wg means total work done minus work done by the gravitational force is the work done by the resistive force, and total work done is equals to change in kinetic energy, so minus Wg. So the work done by the resistive force is minus 8.75 joules. So what does this mean? This means if change in kinetic energy is 1.25, so it means work done by gravitational force is 10 joule. So how can the change in kinetic energy is 1.25? Because the work done by the resistive force is negative, and work is a scalar quantity, so we can directly subtract 10 minus 8.75, and that is why change in energy is 1.25 joules. So now why this work done by the resistive force is negative? Because displacement was downward whereas resistive force was upward, so that is why both are in opposite direction. So if the angle between the force and the displacement is 180 degree, then cos 180 is minus 1 and work done is negative. But for gravitational force, the work done is positive, plus 10 joules is the work done by gravity. Why? Because here the angle, both are in same direction, downward, so the angle between them is, angle between the displacement and the gravitational force is 0, so that is why work done is positive. So cos 0 is 1, and that's the case we have discussed. And so if theta is equals to 0 to 90, then FD will be positive, because you know the quadrants. So in the quadrants, this is all trigonometry values are positive. Here add sugar to coffee or after school to college. So here sine is positive and cos is negative. So that is why in the first quadrant, because cos is positive, so 0 to 90 degree, this will be positive. And then in second quadrant, only sine is positive, cos is negative. So that is why from 90 to 180 degree angle work done is negative. And if the angle is 90 degree between the, like here this coolie was, this is the luggage, and he was carrying this luggage, this potter. So displacement is in this direction, in horizontal direction, whereas the gravitational force is vertically downward, so the angle between them is 90 degree. So cos 90 is 0. So no work done by the gravitational force. So this is what we did, and then we saw the table 6.1, and these are the 4 different units of energy. Now in example 6.3, which was another good example, we did work done by, so there was this bicycle and brakes were applied, so it stopped after 10 meters of distance, so final velocity is 0, and the force was 200 Newton was the force applied. So we know that Newton's third law, force applied by the cycle and force applied by the road. So if cycle is applying the force on the road is also applying the force on the cycle, and both forces are equal and opposite. That is by the Newton's third law. So first part here, we need to find out the work done by the resistive force. So work done by the road, work done by the road. So this R is for the road and C is for the cycle. So work done is equals to F dot D. So work done by the road is equals to force applied by the road on the cycle. So displacement is of cycle. So work done by road is equals to force applied by the road 200 Newton, and displacement of the cycle was 10 meters, and the angle between them was 180 degree, because force applied by the displacement of the cycle in the forward direction, whereas the force applied by the road, which is the friction force, was in reverse direction. So the angle was 180 degree, and that is why work done by the road is minus, because cos it is minus 1, so minus 2000 joules. Now what is the work done by the cycle on the road? So see here, if it was road, work done by the cycle, so force by the road, force by the cycle. If work done by the cycle, then force by the cycle. And whom the cycle, the force applied by the cycle is want to displace, it want to displace the road. But you know, rod is at its position, rod is not displaced, so displacement of the rod is 0. Here the angle was 0 because both were in same direction, force applied by the cycle and displacement of the cycle, but still the work done is 0 because dr is 0. So we have seen that in case of Porter the angle was 90 degrees, so work done is 0, but here the displacement is 0 because the rod is at its place. So this is what we have written here: positive work if final kinetic energy is more than initial kinetic energy, because final is more than this work done will be positive, and that is the case if in terms of theta we understand 0 to 90. And if final kinetic energy, final energy is lesser, then it means work done is negative. So these were the case we discussed. And then kinetic energy, what is kinetic energy? Kinetic is half mv square, so dot product, and that is v cos theta, and that is equals to half mv square. So we did one simple example of bullet also. The initial kinetic energy of the bullet, and then 2 centimeter is the thickness, and then this bullet comes out, and 10% of the kinetic energy was left, only 90%. So final kinetic energy was 10% of the kinetic energy. So we find the initial kinetic energy because Vi and mass was given to us, and final kinetic energy was we have calculated 10% of it, so 10% of 1000 is 100. Now final kinetic energy is half mv square, and we found the value of v square. So pretty simple. Now the next thing was that we again discussed the work done by the variable force, that because we have the formula for the constant force, so how to use this formula to find the formula for the variable force. So we have divided this into the strips, and so for one strip we assume that very small displacement is there, but the force we can assume as a constant. So for one strip we can write that delta W is equals to F dot delta X, and if we add all these small work done in these strips up to this point, then total work done we can calculate, that is approximately equal to this. So now because still there is little bit change in force, so I want this force to be constant, so I need to take this displacement tends to 0, so limit displacement tends to 0, so this sigma is converted into integration. So integration means infinite sum of infinite strips. So when delta X means, because the displacement almost tends to 0, so this will become infinite strips. So integration means nothing but the sum, means adding all, so summation turns into integration when delta X tends to 0, and this delta X will be written as dx. So that's how. And then we did a numerical 6.5 based on it. So this lady is applying a force of 100 Newton, constant force for 10 meters, and she got tired, and then the force that she's applying reduced to 50 Newton. So here it is 50 Newton. So force was reduced to 50 Newton, further 10 meters of distance. So let us draw this graph. So this is the position and this is the force. So force was 100 up to 10 meter, and then the force reduced linearly up to 50 Newton, and the means the position was 20 meters. So, and what about the friction force? Friction force was also up. So friction force is the same throughout 20 meters, and that is given to us, that is 50 Newton, and obviously it is in opposite direction. So if this direction I am taking positive, so this direction will be negative, so that is a minus 50 Newton. So this is the positive work if the force is positive, negative work if the force is negative. So let us find the area of this figure. Above x-axis, there is the work done by the woman. So this is rectangle, so area is 100 Newton into 10 meter, and then this is trapezium, so area of trapezium, and then adding this, so this area comes out to be work done by the woman, so that is comes out to be 1750 joule. That is the work done. So area under the graph is work area between this curve and x-axis is the work. So here the force was negative, so here it is a rectangle, so work done by frictional force is minus 50 into 20, that is minus 1000 joule. Then we did another example, 6.6, and in 6.6 this was the, you have a box here, and then there is a rough patch on the surface, so there is resistive force. So here the surface was smooth from 0 to 0.1 meter, and then this rough patch up to 2.01 meter, and again the surface is smooth. So the resistive force was equals to minus k by x for when the position is between 0.1 to 2.01 meter. So between this, when there is a rough patch, then this is the resistive force, means the force in this direction is minus k by x. So minus k by x, because it is, this friction force is opposite to the direction of the displacement, and it is 0, this resistive force is 0 for the smooth surface when x is less than 0.1 and when x is greater than 2.01. So two branches, so that's what I discussed here, that it has like two branches in the modulus function we have. So f of x is equals to x if x is greater than 0, and f of x equals to minus x if x is less than 0. So if x is 2, then it will remain the same if x is greater. But if x is equals to minus 3, then minus of x, the answer is minus of x. So what is x? Minus 3. So minus of x, and that is 3. So that's how this modulus function work. Not related with this, but just telling you that like we have two branches over here, here also two branches of this. Okay. So now in this question we need to find the final kinetic energy. So this was, let us again revise this question. So yesterday my voice was low, so that is why we are doing the revision once again. So the kinetic energy is equals to work done by the variable force here, that's the formula for the variable force, and the scale. So kinetic energy is, final kinetic energy is minus initial kinetic energy. So this, so here initial kinetic energy was ki, and final kinetic energy was kf over here. So I know the initial velocity half mv square, initial velocity is 2 here, and the mass is 1 kilogram. So just doing it variably as far as possible. So kf and minus ki, so ki will go this side and become positive, and this is the same, so constant will come outside, minus k, and limits 0.1 to 2.1 meters, so limits of displacement. So, and this is 1 by x by dx. So one formula of integration I told you, that integration is x raised to the power n into dx is equals to x raised to the power n plus 1 upon n plus 1. You can write, it's better to write c plus c, constant of integral, this is indefinite integral. And but if it is 1 by x into dx, so students, that is equals to log, natural log x plus c, constant of integration. So this is the formula we need to use here, 1 by x dx, and that is, so this natural log to the base e, we can also write it as ln x plus c. So but here we need not to write c. Why? Because this is definite integral, limits are given. If no limit is given, then only we will write constant of integration, but here the limits are given, so we will write the limits here, and then putting the final value of x minus putting the initial value of x. So that's how we solve it. Now little bit discussion about, sir, what is the meaning of log, because this is the first time I think you are studying log. So log to the base e, and here I am finding it, suppose x is equals to e raised to the power 2, so the answer is 2. Suppose if log to the base 10, so what is the value of log 100 to the base 10? So 100 can be written as, so let me write it once again. So this 100 can be written as 10 raised to the power 2. So log means what is the power if this number is written in the base as this base of log. So 10 raised to power 200 can be written, and the answer is 2. So it's so simple. So now we have two formulas of log. Log A plus log B is equal to log A multiply B, and log A minus B, then log of A divided by B. So now we have to use this formula, log A minus B. So this formula we have used. So that is equals to log A divided by B. So log of 2.01 divided by 0.1. So multiplying both sides by 10, we get 2. So this will be equals to log of 20.1, and this is 2 into. And what is log 20.1? So log 20.1 is e raised to the power 3. Value of e is 2.7. So 2.7 raised to power 3 is approximately equal to 20.1. So that is why log of 20.1 is approximately equals to 3. So I have written 3 over here, and that is equals to 2 minus 0.3 into 0.5 into 3 is, so final kinetic energy was 0.5 joules. Now my target was to find the final velocity. So final kinetic energy is equal to half m vf square, and this we can calculate the final kinetic energy. So I discussed one more thing here, that differentiation, if I want to discuss in physics, we will be dealing with two things primarily. One is the vector algebra and second is the calculus. So in calculus we have two things, differentiation and integration. So differentiation means finding the slope of the curve at a particular point. Suppose this xt graph, so finding the instantaneous velocity at this point. So slope of this tangent at this point, and that is v is equals to dx by dt. So that's where we use to differentiation. Where do we use? When we need to find the instantaneous physical quantity. And where do we use integration? Integration means we have just done that it is the area under the curve. So this is what their physical interpretation is, but algebraic interpretation, this is the algebraic interpretation of integration and algebraic interpretation of differentiation. So integration is anti-differentiation. So it just reverse of differentiation. Suppose you are doing the differentiation of log x. So differentiation of log x is 1 by x. Now doing the integration of 1 by x, you will get log of x back. So differentiation of log of x is 1 by x. Integration of 1 by x back log x. So algebraically they are opposite. So that is why it's not that difficult to find the integration. It's anti-differentiation. And now students, today we have to start the concept of potential energy. So let us start the concept of potential energy. This is very important concept, students. Topic 6.7, the concept of potential energy. So, very important concept. Now, the word potential means the possibility or capacity for action. See, we use two symbols here for potential energy. One is V and another is U. So, here in 11th class, we'll be using this symbol for gravitational potential energy, whereas in 12th class, when there is electrostatic potential energy, we'll use the symbol U. So in some books symbol U can be there, but in NCERT the symbol is V, and we will be using this symbol for the potential energy as per the NCERT. So when the term potential energy comes, directly it comes to your mind. You have studied in 9th class that I have lifted a object to height h, right? Then some energy is stored, so stored energy, right? So that is what comes to my mind, that this stored energy is equals to potential energy. So this comes to my mind, and when I release it, it will come down with a great speed. So because Earth is pulling it towards itself. Now, so potential energy is stored due to the position. Okay. Another thing is that if we discuss about the earth crust is not uniform, and it has discontinuities, and even it has dislocations also, that are called the fault lines. So this discontinuity, this dislocation, and these fault lines in the earth crust is like the compressed springs. This is something like, this is your spring, and you have compressed this string. So compressed string, if you just leave this string, this will go back. So here also potential energy is stored in this spring. So here also in fault lines, potential energy is stored in the fault lines. So, and when you release it, so here also due to this potential energy, we have earthquakes when these fault lines readjust themselves. So this stored potential energy. So the important thing is, very important thing, students, just write it down, that the potential energy is the stored energy. Potential energy is the stored energy by virtue of the position, or you can also say configuration of a body. So what does this mean? So primarily here we will be assuming that this is earth and I have a body over here, so which is near to, still this is not up to the scale, this is the radius of the earth, and so RE I can write, and this is height h. So this height h, so height I am taking is very less than RE, so very less than RE. So that is why I will be taking G as constant throughout near the surface. So G is constant, I will be taking due to this reason. So okay, so students, when the potential energy is due to the, see this was your earth, and this was the position or configuration. So if I change this configuration, if I bring this object over here, so the potential energy will be different. So it is due to the position or the configuration of the body. And important thing, so this was the first thing, and the second thing that you need to note is that if the body is left, so students, see this thing you are going to study again in chapter in class 12th. So when we will study here, we will be studying gravitational field, and in 12th class we will be studying electromagnetic field. So the concepts will be the same. So you need to understand this concept well. And when the body is left to itself, so if you leave this body over there, what will happen? The body left to itself, then it releases. So the body releases this stored energy. Release this stored energy in the form of kinetic energy. So in electromagnetic field, suppose this is positive charge and this is again a positive charge. Now you are bringing this positive charge near to this, so they are like charges, so there will be repulsion due to electromagnetic force. So now, or electric force purely here, no magnetic but electric force, so repulsion due to the electric force. So you have brought this charge over from here to here. So now potential energy is stored here in this charge. Now leave this charge, this will be repelled, and again it will possess now kinetic energy. So same is the case here. You are doing the work against the gravitational force, and that is why the energy is stored. So whenever you do work, so here you were doing the work against the electric field, and here you were doing the work against the gravitational field. So whenever you do the work against the gravitational field or gravitational force or electric force, then the work that you are doing is stored in the form of potential energy. So this is what we are going to study in detail. Now, the gravitational force acting on a ball, this is ball of mass m, so it is always downwards towards the earth, and the gravitational force, I can write it as Fg, so here I need not to write G again and again, so I will be using F, and that is equals to mg. I also call it weight of the body also. And as I told you that G can be treated as constant because the height that we will be taking will be lesser than, very less than Re, so we can ignore the change in variation of G. Now let us, like we have already done, that I have raised this, so this ball was over here of mass m over the surface, and I have raised this ball to height h. So of course by the external agency, so or applied force you can say, so this is raised by the applied force, or you can say force by the external agency, external force. So these are the two ways of writing the external force or applied force. So what is the work done by the external agency? So work done is equals to, the work done is equals to force into displacement. So what is the force? So the force here is equal and opposite to this. So I am actually taking this body very slowly so that the initial velocity is equals to the final velocity. We'll study about this. So students, this whole work done will only be changed into potential energy when I'm taking the ball upward with very small velocity, infinitesimally small velocity, such that initial velocity is equals to final velocity. So if both are same, then only the work done by me will be stored as total potential energy. So this is the case that we will be taking. So the forces are actually equal and opposite because there is no change in velocity, acceleration is 0. So I can take this force as mg, and that is equals to, and the displacement is h. So work done is by the and what is the means this F external, so this is the work done by the applied force. So WA, let me write it a little bit. So this is WA, work done by the applied force, that is mg. Now applied force was in upward direction and displacement was also in upward direction, that is your h. So that is why there is an angle of cos 0. So that is equals to mgh. Now what is the work done by the gravitational force? See, gravitational force was acting downwards and displacement was upward. So what's the angle between them? So Fg, that is same, mg, height is means displacement also, but here the angle is cos 180 degree, means equal and opposite. So this displacement and this Fg, so the angle between them is 180 degree, and cos 180 is minus 1. So that is why work done by the gravitational force is minus mgh. So this you need to see, students, always that, and we have discussed this case earlier also. So now so these are simple concepts, very simple, just logical thinking is involved. Now as this you can clearly see this potential energy is a function of height. More is the height, more is the potential energy. So I can write this potential energy as gravitational potential of the energy of the object is a function of height. So this is gravitational potential energy is a function of h, and we have seen that this equals to mgh, but that is equals to the, if I talk about the work done by the gravitational field, then this is negative, multiply both sides by -1, and I get Wg is equals to mgh. So mgh is equals to, so this is negative work done by the gravitational force. You can write, whether you write g or not, I told you it doesn't matter, it is for the by the gravitational force. So h is variable. So students, in future you can assume f as fg. So fg will be, I will be writing as f in your book, fg is written as f, and work done by the gravitational force is written as w. So remember these two things, that's how. So gravitational force is written as f, and work done by the gravitational force is written as w. So here mgh is equals to negative work done, because displacement was upward and force was, gravitational force was downward. So now if we write the, if we do the derivative of this, what do we get? dv, differentiating it with respect to h, what do I get? So dv by dh is equals to, put the value of, so differentiating both sides, or you can simply put the value of v by h here, so we get d by dh of mgh. Now m is constant, g is constant, so they will be outside, and this is dh by dh. So power is 1, 1 will come in front as coefficient, and 1 minus 1 is 0, and h plus 0 is 1. So that is why mg 1. So that is mg1 means mg. So now this is equals to minus, so fg is equals to the okay, so that is equals to mg, and mg is the force, right? So f is equals to mg, so that is the gravitational force, but this will be negative. So why this will be negative? Because the gravitational force is downwards. So because the gravitational force is downwards and the height I was taking was upward, so both are in opposite direction. So that is why it was it is negative. So here mgh is so vh is equals to mgh, and it is equal to negative work. So gravitational force will be equals to this, or I can write further that gravitational force is equals to, either I write negative sign here or here, minus dvh by dh. So that is the gravitational force, and that is equals to minus mg. So I can write it like this also. So this negative sign indicate that this force is downward, because upward direction I have taken positive. So if force is upward, it is positive, and the downward direction I have taken negative. So students, let me tell you, sir, why you are not writing the symbol f as in the vector form? Because in chapter 3 and chapter 4. In chapter 3 it was motion in a straight line. So whenever motion is in a straight line, there can only be two possible direction. One is positive, one is negative. So I need not to use the vector sign. I can simply tell the direction by the negative and positive. Whereas in chapter 4 it was motion in a plane, so it can be any direction, so I need to use the vector. So whenever it can be any direction, I will be using the vector, but whenever it will be only the motion in a straight line, means motion along a straight line, I need not to use the vectors here. So this is a vector, of course vector quantity, and the direction is given by this minus. So direction, this is negative direction, so this is the direction of Fg. Now we'll do a derivation. We'll derive important result, what that result is about. So now the ball is released. The ball was at height h and it is released. This is my ground. It is going to hit the ground with velocity v. So here the velocity was 0 and the ball hit with velocity v. Now we know the formula, v square minus u square is equals to 2g h. So u is 0, so that is equals to v square is equals to 2gh. So now multiplying both sides by half m. So what do I get this side? Half mv square is equals to half m into 2gh. So this cancels out and this comes out to be the final kinetic energy. So this is your final kinetic energy and this is your mgh. That was your potential energy. So that was your initial potential energy. So means the final kinetic energy is equals to the initial potential energy. So it means whole potential energy is converted into the kinetic energy. So it means the work that you did was stored up in the form of energy, and when the external constraints were removed, then it comes down with velocity v, so the kinetic energy. So that's very important relation. Now another thing is that mathematically students, we are going to do these things again and again, means we will be applying this, so it will be very easier for you. So maintain your cool and calm, keep on making your notes. More will be doing these things, will be more familiar with them day by day. So the potential energy mathematically, if I want to write, it can be written as we just did here, d by dh is equals to, we have written it minus fx. So fx is equals to this. So we have already written this. So I'm rewriting it again. That. So here it was for height h. Now I am taking it for, means I can write it for any one-dimensional motion. Means general case I am taking here. So instead of fh, I will be taking fx is equals to minus d by dx v. Now I will be integrating both sides. So integrating both sides, I get, so this is fx. So dx, this can be, means you can write this as fx dx is equals to minus dv. Okay, so integrating both sides with respect to x. So tell me the limits, what I am going to take, the limits of x position, so xi minus xf, and that is equals to, now this is minus dv. So which limits? So I am going to take the limits of potential energy, so initial potential energy minus final potential energy. So this can be written as, so this is the work done, and this work done will be equals to, so you know the integration of dv is, we did it, that is v, and this is vi, because we know the integration of dx is equals to x. So vi, vf, and this can further be written as, put v is equals to vf minus v is equals to vi. So that's work done is equals to, so final minus initial delta v. So work done comes out to be, so this minus over here, so this is minus here, and then again minus. So let me write it once more. So we need to be very particular about this sign negative, and this comes out to be v integration vi to vf, and that's w equals to minus vf minus vi, and that comes out to be work done is equals to minus delta v. So this is what we have discussed earlier also, that work done is negative. So that is the same thing, minus w, you can write it as height is, there's a change in potential energy, so this you can write it here also. So that's the same thing, but we have derived this relation that the work done by the gravitational force is actually the negative of the potential energy, or better you say that change in potential is negative of the work done. So, and we have done that, suppose this is vertical height h, and I have dropped this ball from here, this frictionless surface, and this is mass m, and the body is going to hit, this ball is going to hit the surface with a velocity that is equals to, with the same v square minus u square is equals to 2gh. So u is 0 here, so with the same formula, v is equals to v square is equals to 2gh, and v is equals to under the root 2gh. So if the work done or the kinetic energy, so here this kinetic energy does not depend on the path taken. So students, now we need to understand that the forces are of two types. One is conservative force and another is non-conservative force. So in conservative force, the work done by the conservative force, so this is conservative force, this is non-conservative force. So work done by the conservative force does not depend on path. So the work done by the conservative force doesn't depend on path, but depends on initial and final position. But here work done depends on path. So frictional force is the example of non-conservative force, whereas for conservative force the example is gravitational force and we will further do spring force. So these are the examples of conservative force where the whole work is converted into the potential energy. I told you one condition, that initial velocity, when you are storing this into this whole work done into the potential energy, then you need to take this body infinitesimally small speed, taking upwards with infinitesimally small speed. So students, this is the base for what we are going to do in this chapter next. So, and another important thing we studied, that kf is equals to ki. So this also significant, very important thing, principle of conservation. So these are the two prominent things that we are going to do. So principle of conservation of energy, this thing was telling us, and then this thing was telling us the conservative force. So conservative force, and so this is about the conservative force. This gravitational force, the conservative force, tells something about it, and this tells about conservation of energy. So on these guidelines we will proceed our lecture tomorrow. Thank you students for watching this lecture. In the future, in the next lectures, we'll make this concept very simple when we'll apply it. And until then, goodbye. See you tomorrow at 5:45.